Nature is made possible by public television stations, your gas company and America's gas industry, bringing natural gas through 1 million miles of underground pipelines to 160 million people, fueling factories, heating homes, and cooking meals.
Hi, I'm George Page, and this week on Nature, our story is about the remarkable work of a pioneering American scientist. Man, as it turns out, was not the first creature on Earth to develop highly sophisticated methods of chemical warfare. Insects did that millions of years ago. But until recently, very little was known about nature's chemist of the insect world. Much of what we know now, which you'll see stunningly illustrated, comes from the experiments of Professor Thomas Eisner and his associates at Cornell University in Ithaca, New York. Tom Eisner's world is largely invisible to the naked eye, but he shares that world with us in our film, Secret Weapons. Explorations of our lively planet can now extend down into a world of the infinitely small. With new instruments, new techniques, and new ideas, we can rescan familiar and unfamiliar life forms. Through our new eyes, we enter an alien environment. Here, the struggle for existence is no cliché. It means possessing ways to ward off attack, weapons that can, at a moment's notice, spring to the defense of a life. The setting, Arizona, summer 1982. The explorer, Professor Tom Eisner. His passion, the secret world of insects and the hidden weapons they use in defense. Insects, it's been said, will inherit the earth. A larva can instantly burp up its droplet of resin, and the repellent takes effect. The smell drives off the ant, and if it gets glue on its legs, it may get permanently entangled. The droplet is eased out, but danger over is sucked in again and held for later use. Few of us realize how many plants are protected by their own chemicals. The milkweed is no exception. It squirts out its poison when injured, but again, some insects are undeterred. Some caterpillars, including those of the monarch butterfly, even accumulate the chemicals in their bodies and retain them as they grow and develop. So, as adult butterflies, they themselves are laden with the poisons, beneficiaries of what they gained in their youth. Many insects use the same strategy. If an insect has evolved a way of being insensitive to a plant's poisons, then why not use these poisons in its own defense against others? Eisner and his colleagues have made a detailed study of one moth that lives on a poisonous legume. And the research turned out to have an unexpected twist. The moth is called Utathiza.
We first noticed that the caterpillars of Utathiza competed for the seeds of the plant. That's where the poisons are concentrated, and they're very potent. Chemically, they're a type of alkaloid, bitter and highly toxic to us. The caterpillar chews its way into the pod and eats the whole seed. When the larvae are crowded on the plant, there may be winners and losers in this competition. Those best able to break into the pod may end up with the most poisonous alkaloid in their bodies. And as an adult, the moth retains them. Unlike many other moths that remain hidden by day, Utathysa risks exposure. The poisonous alkaloids are its defense, the coloration its warning. Red, white, and yellow make it extremely conspicuous. Bright and attractive, it lives in a world full of many dangers.
Utathysa has problems with spiders. If it flies into an orb weaving spider, it might be eaten. It may have problems with bats. And of course, it may have problems with birds. Birds are among the major enemies of Utathysa. They feed on many insects. And these scrub jays in particular are aggressive toward insects that come within sight.
Eisner tested the moth's palatability. He offered the scrub jays edible and inedible insects. First, a tasty moth.
You like a moth? Would you like to get a moth?
It's eaten with relish. Now the jay is given a choice: edible insects in the palm and an Utathysa between thumb and forefinger. All but Utathysa are taken. The warningly colored moth is undoubtedly seen but ignored. It will survive another day. The gourmet jay remains selective and only accepts the best. Another edible moth is grabbed and eaten piecemeal.
Pulling the wings out, they often do that. Wings are thus just scales and paper, essentially. It's like taking the wrapper off a candy bar. The head. Thorax and body. That was the good part. Now, you liked that, didn't you?
Utathysa continues to be ignored, whether offered by itself or in combination with edible insects. It survives an occasional peck, but is obviously well protected. The research didn't end here. It developed to reveal that in the courtship of the moths, the poisonous alkaloids have another intriguing role to play. For all his work on the moth's defense, he had to breed them in great numbers. When in their separate boxes, both male and females are relatively inactive, but once united in an artificial nuptial chamber, they perform a courting dance quite naturally. With his frantic fluttering, it's hard to see what the male does.
The dance that the male performs around the female is too quick to really follow with the naked eye. So we resort to photography, flash photography, which catches events in a nice frozen fashion. And it was by means of this flash photography that we eventually learned exactly what goes on when these two are interacting.
Eisner took dozens of photos, always trying to catch the male when closest to the female. Some pictures were timed just right and gave him the answer. During the flutter, the male opens up his abdominal tip and exposes a hidden structure. This he brushes against the female. The microscope revealed that he has two brushes for that purpose, splayed at the moment of contact. And every bristle of the brush is coated with a secretion. It's at once an aphrodisiac and the carrier of a very special message. By greatly increasing the magnification, he was able to find exactly where the secretion was coming from. It was oozing out between the sculpturing on the surface from tiny pores.
I asked some friends who are chemists to analyze the secretion, and they found it was derived from the poisonous alkaloid eaten by the caterpillar. This set us thinking. We speculated that the amount of defensive chemical the male caterpillar stores will, in due course, be measured by the female moth by judging how potent his aphrodisiac is.
The males were raised on an artificial diet with no alkaloid. They grew up into normal-looking adults, but they had no defensive chemical, so no aphrodisiac either. The next step was to see whether the female responded in a different way to males with the aphrodisiac and those without. The female is presented with both. She initiates courtship. She climbs up a plant and emits her sexual attractant, which drifts downwind. A male flies in and begins his fluttering dance. Not surprisingly, the test showed that the female preferred males with the aphrodisiac. She was more likely to mate with them. They were also best protected chemically. Eisner believes that females favor males which are the best at storing poisonous alkaloid. This ability might be inherited, so it will also benefit their offspring. Their caterpillars will be better alkaloid gatherers and have a better chance of survival. At night, our eyes are blind to most natural dramas played out on the woodland floor. But there's some insects that flash out their own picture of life and death in a visual Morse code. The signals speak not only of courtship, but deceit, and reveal a new dimension in the use of chemicals in defense.
I've just collected a net full of fireflies. Fireflies are the one insect that one can see at night. It's an insect that every American child knows. The males and the females are active at night trying to find one another. The ones I've collected are all males. They're flashing, and they ordinarily flash when they fly, because in fact they're announcing their presence to the females.
The females sit waiting on a plant and answer the males with a welcoming flash. It's a courtship duet in lights. The male responds to her reply and flies down to mate. Each species of firefly has its own individual code of flashes. A female identifies her own male by the rhythm and number of flashes. Then she answers after a specific time. Few mistakes are made and compatible partnerships are forged. The code of the visual duet is precise and ensures that the mating encounters are of the right kind. But encounters of the wrong kind do occur. There are fireflies, female fireflies, that deliberately set out to break the code. During the courtship, they attract their own males for mating from the many signaling above. But these same females can deceive the males of other species by imitating their females. They mimic another's courtship flash and lure down a stranger, but not for mating. She is a femme fatale, and the male has been enticed to his death. For a female about to lay eggs, prey caught so easily is certainly a boon. But this elaborate counterfeit is not just to obtain food. There's an additional bonus. It was discovered that the males she eats are full of defensive chemicals, this time poisonous steroids. The femme fatale has no steroids of her own. She's defenseless. Her skill is to acquire them in this ingenious way. She builds the male steroids into her own body. Now, she too is poisonous and protected. She's most vulnerable when searching for a place to lay her eggs. A wolf spider waits in ambush. Touched and tasted, the female firefly is rejected, saved by her newly acquired steroids. They seem to leave a nasty taste, but neither spider nor firefly is permanently harmed. There are times and places when working at night, we would welcome having our own built-in chemical defense against midges and mosquitoes. We rely on creams and lotions and a wary eye on the bigger beasts that bite. Of all the insects that are chemically protected, there's no doubt which takes the prize: the bombardier beetle. Its weapon exploiting nature's chemistry set, making full use of the same fun and games that mischievous children might in making their first stink bombs. But among the many millions of insects, the game is hugely varied and played for real. This is an arms race between predator and prey, which we have scarcely started to explore. The scenes at the end of our film showing the bombardier beetle and the spider were actually shot on the last day of filming near Portal, Arizona. That was the end of the film, but it wasn't the end of the day's excitement. After dinner that evening, Tom Eisner decided to take one last look around before turning in. Cameraman Roger Jackman went with him. And standing near a small pond, Roger thought he saw something quite remarkable. He called to Tom, and together they observed the following strange sight. Thousands of spadefoot toads, just emerged from the tadpole stage, were climbing out of the water and sitting on the muddy shores of the pond. They were all very small, just under an inch in length. Suddenly, Jackman saw one of them almost disappear into the mud. Jackman and Eisner then noticed that many of the toads had been pulled down into the mud, with only their heads sticking out. Others were dead or dying. When Tom and Roger tried to pull a toad out of the mud, they felt a strong resisting force. Guessing that some unseen predator lurked beneath the surface, they dug into the mud but found nothing. Whatever it was seemed capable of quick, evasive burrowing. Eventually, Tom Eisner decided to take a sample of the mud back to his laboratory for testing. There he found a large grub-like insect larva, the early stage of a type of horsefly. About as long as the toads, the larva, as Eisner discovered, can grab any toad that settles above it with its hook-like mandibles and pull it beneath the surface. There it drains the poor toad of its blood and body fluids. Tom Eisner and Roger Jackman published their findings. It was the very first time this natural phenomenon had been recorded in a scientific journal. For those of us who work on nature, it's rewarding to know that sometimes the production of our films results in a new scientific discovery by our colleagues. I'm George Page for Nature.
Nature is made possible by public television stations, your gas company, and America's gas industry, developing new sources of gas energy and ways to use gas more efficiently for more than 160 million people across America.
Next week, we go to India, to the Bharatpur National Park, in one unusual year when the monsoon rains fail to arrive. The Missing Monsoon, our film next week on Nature.